Welcome to the Handley Page Lecture for 2022, co-sponsored by Cranfield College of Aeronautics Alumni Association and the Royal Aeronautical Society. My name is Dougie Hunter, and I'm the chair of the Cranfield College of Aeronautics Alumni Association. A couple of minor health and safety items that I need to raise with you. If we're not intending to have a fire alarm, if there is a fire alarm, that's the door we all head out of. And if you're still in here when I go out the door, tough. I'm leaving you. I'm a Cranfield College of Aeronautics alumnus from 1985, and I've had an ongoing association with the university for many years since then, including as a member of the University Council and as a speaker at this lecture a few years ago. The Handley Page Lecture is dedicated to both the Handley Page Company and Sir Frederick Handley Page in particular. Sir Frederick was a member of the 1943 Fedden Committee and was instrumental in establishing the Cranfield College of Aeronautics in 1946. He subsequently served on the College Council and was a past president of the Royal Aeronautical Society. Sir Frederick passed away in 1962, but Cranfield and the Royal Aeronautical Society wished to honour his memory by creating the Handley Page Lecture, the first of which was delivered by His Royal Highness the Duke of Edinburgh on the 21st of May 1963 and was titled Education for Technology. I would like to introduce you now to our speaker for the Handley Page Lecture for 2022, Mark Cousin. Mark is Chief Technology Officer with Universal Hydrogen. Mark is another one of those people that I've known a lot longer than I really wish to remember. We've worked together for quite a lot of years over the last more than 30 probably. Mark has over 3 decades of experience designing and developing future aircraft, most recently as CEO of Airbus Silicon Valley Innovation Centre, Acubend. Mark is a 20-year veteran of Airbus, where he was the head of flight demonstrators in the CTO organization, leading a team responsible for launching and operating flight demonstrators to develop technology solutions faster than in a normal research and technology organization. He also served as the CEO of Airbus Alpha XO, the exponential organization used to facilitate the speed up of execution. Prior to this, Mark served as the technical director for the Airbus Beluga XL, where he led a team that designed and built the next generation of an outsized transport aircraft for Airbus based on the A330. Mark is a graduate of Southampton University, where he studied aeronautics and astronautics before joining British Aerospace Regional Aircraft in the Future Projects Department. Mark's lecture this evening is around a subject that I think is all very relevant to this moment in time, and is titled Flight Testing and Integrated 1 Megawatt Hydrogen Fuel Cell Powertrain. Mark.
Thanks. Can everybody hear me? Okay. So as you said, I'm going to take you through the experience that we're going through at the moment at Universal Hydrogen. I'll do a little bit of promotion of Universal Hydrogen as a company as well. We're in the process of flight testing a 1 megawatt powertrain on a Dash 8-300. So the aircraft you see there is actually an ATR 72. That's an aircraft we have in Toulouse. But I'll take you through where we are with both Universal Hydrogen, why the company was established, and what we're doing to advance the state of the art in hydrogen-powered aviation. So maybe just to start off with, what the company is about. I think it's fair to say that we're a world-class team. With a lot of aviation and energy experience. The company was founded by Paul Eremenko, who was the founder and CEO of Universal Hydrogen. Paul's previous experience was as CTO for both Airbus and UTC, I met Paul probably 7 or 8 years ago when he was CTO at Airbus. And we have a strong team of people on the executive management team. But you'll also see we also have a very strong advisory board, including Tom Enders, one of the former CEOs of Airbus, Carl Burleson, who's a former deputy minister of the FAA, Patrick de Castelbajac, who's a former CEO of ATR. So we have a very strong team of executives and an advisory board. We also have a very strong investor base. So the company was founded in 2020. So it was a child of COVID. It was founded in a beach house on Venice Beach, with the 4 founders working from a house in the just as COVID took hold. Our lead investor is a very well-known venture capital company called Playground, and we have some very strong financial investors. Big Coatue is a big New York hedge fund, and Tencent is a big Chinese investor. Mark Benioff is also an investor. He's the CEO of Salesforce. And you can see we also have a number of very strategic investors, including Airbus Ventures, GE Aviation, and Toyota Ventures. We also have Fortescue Future Industries and Plug Power, who are, not coincidentally, 2 of the biggest producers of green hydrogen in the world today. And we also have 3 airlines who are investors in the company. JetBlue, Walsing Matilda Aviation, who trade under the name of Connect, who is a company setting up as a feeder airline in the US. And just recently, American Airlines invested directly in the company. So we have a very strong investor base. We've raised around 100 million of capital so far. We'll be raising a Series C round early next year to take us into the next phase. So maybe just to talk about why was the company formed? The company was formed really to get aviation on a path towards meeting the Paris emissions goals. I don't know how many of you know what the Paris emissions goals are, but essentially it's to get the worldwide economy to a net zero emissions target by 2050. And what you see on the left-hand chart there is the roadmap that was agreed at Paris to get various industries to zero emissions by 2050. What you see on the right is what is happening with aviation. Aviation historically is growing exponentially. It doubles in passenger kilometers flown roughly every 15 years. It's been a little bit affected recently by COVID, but historically we will see a doubling of passenger traffic every 15 years. And what you see on there is the current predictions of where aviation is committed to be by applying new technologies and improvements in operations. And essentially, the current aviation outlook is a small or still significant increase in emissions compared to the emissions today. So without radical change, without new fuels in the aviation business, aviation is not going to get to the Paris goals. So if we don't do something pretty fundamental in this industry, we are either going to face a situation where the industry becomes something of a pariah in the world, because the percentage of emissions from aviation, although they're relatively small today, around 3% of global emissions, they're going to be growing in percentage terms quite rapidly as other industries decarbonize. So the real danger for aviation, if we don't do something about emissions, is that the authorities will do something about emissions by restricting passenger traffic. And I think everybody agrees that that will not be good for the world economy. It won't be good for it won't be good for society as a whole. So we really feel that there has to be a major effort made in the industry to bring new fuels to the industry and reduce the carbon emissions by 2050. And we can't afford to wait. We have to start doing something now. So you've probably all heard about SAFs, so-called sustainable aviation fuels. SAFs clearly play a part in decarbonizing aviation because they're the sort of holy grail drop-in replacement for kerosene, for Jet A1, for the dinosaur juice that we use today. But one of the real problems with SAFs is that the only scalable solution for SAF in the long term is synthetic fuels, so-called power-to-liquid fuels that are manufactured from scratch. The sustainable aviation fuels that we are using today that are manufactured from recycled carbon sources like used cooking oil and wood chips and things like that, they have no possibility of scaling to feed the whole aviation industry. So what you see here on this chart, I won't go through it in great detail, is there are really two ways of fueling aircraft in the future. Either you use liquid hydrogen, which is relatively easy to produce. It's relatively energy efficient. So what we show here is, coincidentally, the energy contained in a kilo of hydrogen is almost exactly the same as the energy contained in a gallon of kerosene, which is a pure coincidence, but it makes comparisons relatively easy. So what you see here is you need something like 4 times as much energy to produce the same amount of energy stored in a power-to-liquid fuel as you do to have the same amount of energy stored in liquid hydrogen. Now, there are some clearly a liquid hydrogen aeroplane has some disadvantages. The liquid hydrogen takes up a lot more volume than synthetic fuels, but it also has some very significant advantages. So we believe that particularly for regional aviation, which is what we're tackling initially, and for shorter range single-aisle aviation, liquid hydrogen is going to be the solution for that market. And the real key to this market is dealing with the emissions of single-aisle aircraft. So the 737 and the A320, those families of aircraft account for 60% of aviation emissions globally. And though both of those airplanes are going to be replaced in the mid-2030s, so we have an unmissable opportunity in the next decade to influence the design of the replacement of those families of airplanes to make a real impact on carbon emissions in the future. And that's really what we are trying to do at Universal Hydrogen by demonstrating that it's possible to do something with current technology and existing aeroplanes to trigger the debate about where the industry has to go for the replacement of single-aisle airplanes. So what we are trying to do at Universal Hydrogen is essentially what Tesla did for EVs. One of the biggest problems with hydrogen in aviation is how do you get hydrogen from the producers of hydrogen, and the obvious producers of hydrogen as renewable energy expands exponentially are renewable energy sources. So it depends on the country, but in California you have an excess of solar energy during the day. In the UK you have an excess of wind energy at night. In France you have an excess of nuclear energy during off-peak hours and nighttime. So there's plenty of low-cost off-peak renewable energy around. And as renewable energy expands, the amount of renewable energy will expand dramatically. The one thing that doesn't exist is the infrastructure to get that renewable energy from the producer to the consumer. And that's really where the universal hydrogen model comes in. Trying to duplicate the let's call it the pipeline type approach, which is used today to deliver kerosene to airports, is something which will take trillions of dollars of investment and decades to put into place. And it has to be duplicated. You can't convert existing infrastructure because both kerosene and hydrogen will have to run alongside each other for a significant number of years, probably even decades. So what we're looking at is having a solution where you have a modular solution. We load hydrogen into modules at a factory filling site close to renewable energy sources. We then transport that fuel to the airport using the existing dry freight network that is gradually decarbonizing. And then instead of trying to refuel the aeroplane, and some of you may be aware, refueling an aircraft with liquid hydrogen is a major challenge. It's not like pumping gas. So what we're looking at is looking at what other things are airports good at. Airports are good at really three things. They're good at handling passengers, they're good at handling existing fuel, but they're also good at handling freight. So what we're looking at is loading the fuel onto the aircraft like freight, like cargo that is loaded onto aircraft today routinely when the aircraft are turned around at the airport. So this is a demo that we did recently. This is an ATR 72 that we have in Toulouse, in our Toulouse facility. This is both our reverse engineering aeroplanes, so we're reverse engineering the ATR 72-600 as our first conversion vehicle, but it's also the vehicle that we're doing the loading demos on. So you can see there, this is a demonstration of the two liquid hydrogen modules that we need to load into the rear of the aeroplane to provide enough fuel for the flights that these aircraft perform. And as you can see, the modules, they weigh about 600 kilos each, and they're loaded using existing loading equipment. That loader is actually much bigger than we need to load these size of modules. They're basically the same base plate as you'll have on an LD3 container. So it's a standard format container that gets loaded into the aircraft, like cargo, and then just connected to the system. So a couple more pictures. That's what it looks like when they're in the aeroplane, and they're obviously designed to maximize the cross section of the ATR 72, which is our first conversion target. So what's different about what we're trying to do? Our general approach is we are not trying to invent any new technology. We're trying to take existing technology and apply it or mature it for use in aviation, and that includes the liquid hydrogen storage module. So we're trying to do engineering, not science. We're not trying to invent anything new. We're trying to adapt things which already exist for use in the aviation industry. So what we're talking about here is a conventional double-walled Dewar liquid hydrogen container. So you have a container which has a vacuum-jacketed, double-walled metallic structure. The liquid hydrogen is contained inside and is insulated from the heat, the external heat. And we can achieve multi-day hold time without any need for venting. So we have no need to release any hydrogen from the container between the point when it's filled at the renewable energy site and the point when it's loaded onto the aircraft and used. That's really key, because if you have to release any hydrogen, then there's a risk of creating flammable mixture. So that's really the key to this technology. It's a zero boil-off technology, but it's not using anything it's not using anything anything fundamentally that fundamentally doesn't already exist. There's a lot of engineering to be done to make it suitable for aviation, but the basic technology is not new. So, coming on to the subject, the subject of the presentation here is we're looking to flight test the first 1 megawatt sized hydrogen powertrain demonstrator. So what you see on this slide here is on the right hand side you see the aeroplane that we're in the process of converting. So we intend to fly this aircraft by the end of this year. So that picture you see there is now already somewhat out of date. The build is much more advanced than that picture, which was probably taken a couple of weeks ago. So essentially what we're flying is the same basic configuration that we will look to certify as an STC retrofit for existing aircraft. But what we're flying on this demonstrator, we keep the Pratt & Whitney 123 turboprop engine on the left-hand side of the aeroplane, and we're retrofitting the right-hand powertrain on the engine with a hydrogen powertrain. The only thing that's contained in the fuselage is the hydrogen fuel. In this case, it's gaseous hydrogen, so we're using gaseous hydrogen modules initially. We will fly our liquid hydrogen solution next year. But the initial flight tests we're doing with gaseous hydrogen, which is perfectly suitable for flight testing, but is not a solution for a production aeroplane because gaseous hydrogen containers are just simply too heavy. We can't achieve the mass fractions that we need to do to be able to carry enough hydrogen in the aeroplane. So you may ask the question as well, why are we flying a 1 megawatt powertrain? This class of aircraft uses a Pratt & Whitney 100 series engine, which are around a 2 megawatt powertrain. The reason we're flying a 1 megawatt powertrain is it's the biggest powertrain that I can fly with a motor directly driving the propeller. So we have no propeller reduction gearbox in this powertrain. But it's essentially exactly half the powertrain that our converted aeroplane will use. But it means we can fly a year earlier than we would have been able to do if we were designing a propeller reduction gearbox. So a gearbox is not difficult technology. It's not complex. It just takes a lot of time to get a gearbox designed and manufactured. And we wanted to get this powertrain in the air as soon as possible and start to understand what the challenges of this type of powertrain are. So I'll run through a few of the challenges. So we're using a 750 kilowatt electric motor, which is supplied to us by a company based in Seattle called MagniX. They're currently probably the most advanced in certifying a large electric motor under CS23. It'll have to be CS25 for this class of airplane. As I said, we then have a direct drive propeller, so we have a custom designed Hartzell propeller, which is driven directly by the MagniX motor. We have a megawatt worth of fuel cells installed on the airplane. Those are currently supplied by one of our investors and partners, Plug Power. But the key is that all of the powertrain is integrated into the engine itself. The only thing we have in the fuselage is a flight test installation and the fuel, which is the same configuration that we will have on the conversion that we intend to offer to the market in late 2025. So this is our 1 megawatt Iron Bird. This is functionally exactly what we'll be running on the Dash 8-300. So the first thing everybody says when they look at that is, oh my God, how does that fit in the nacelle of a Dash 8-300? I can assure you it does. I'll show you later. So this Iron Bird has been running now for about 6 months. 1 year ago, we had a bare trailer with a blue steel frame on it and nothing else. So we've gone from nothing to a fully functional Iron Bird that is running in exactly the functional configuration that the aircraft will fly in next month at Hawthorne as we speak. In fact, I think they didn't run yesterday because for the first time in a long time it was raining so heavily in LA that they couldn't actually run it outside because it was raining so much, which is good for California but not good for us in the short term. So what does the architecture of this system look like? So as I said, we have an electric motor, or in the terms that we use with the FAA, an electric engine. So that electric engine drives directly the propeller. The electric engine is provided with 800-volt DC power directly from the fuel cells. So the fuel cell system provides DC power directly to the inverters, which convert the DC power from the fuel cells into AC power, which drives the electric motor. That's fundamentally different from any other fuel cell powertrain that I think you will have come across elsewhere. Almost every other fuel cell powertrain uses what so-called buffer batteries. So you essentially have a battery driving the electric motor and a fuel cell charging the battery. On an aircraft like this, we cannot afford to do it that way because we can't afford the mass of a 2 megawatt battery, which would weigh nearly a ton per side. And then behind that, a fuel cell is a very simple device. There are no moving parts. You basically have to supply it with compressed air, hydrogen, and it produces direct current voltage. So one of the real challenges of a fuel cell electric powertrain is what's shown at the bottom, the thermal management system. A fuel cell is actually quite efficient compared to a gas turbine. We get thermal efficiencies from the fuel cell of above 50%, which is almost double what you're getting from the gas turbines, the small gas turbines that this is replacing on an aircraft like the ATR-72. But it still means that we have as much heat energy to reject through the coolant as we deliver to the motor. So we have 2 megawatts of power, or in its flight test case, we have a megawatt of power going to the motor, but we also have a megawatt of power that we have to reject, of heat energy that we have to reject. And that's where the real challenge comes. So this is a schematic now of what the hardware you saw on the Iron Bird actually looks like installed in the Dash 8. So there you can see all of the functional components that are installed in the Dash 8, installed in the aircraft, and I'll go through each of them in turn. But you can see that it actually fits in the engine nacelle. Okay, so I guess the heart of the system is the electric engine, the electric motor. So what we're using here is a development of the Magni 650 electric engine, which has recently flown on the Alice electric aircraft you may have seen that flew fairly recently. That's actually flying from the same hangar that we're building the Dash 8-300 in. That's a battery-powered aeroplane, so but it uses the same basic electric motor. This is boosted to produce, in our case, 750 kilowatts at 2,300 RPM. And as I said, is directly driving a propeller, which is derived from the propeller used on a TBM 900. So it's an oil-cooled motor. You can see on the right-hand picture there. That's the engine on the test stand at MagniX in Seattle, and the motor on the left there is the motor that we will be installing in this weekend, I think, on the aircraft in Moses Lake. So that's I guess the heart of the system. That's what generates the power. That's what drives the propeller and produces the thrust. But that's probably the easy bit. that's the easy bit of the system. The more complex part is the part behind the electric motor that provides the power. So fuel cells. I don't know how much you know about fuel cells. This is we're using on the aircraft today a plug power fuel cell stack. So these are typically produced today for ground applications, either transport applications. So there's a lot of work going on to use fuel cells in trucks and big mining vehicles and so on. But they're also used in static applications for data center backups and backup power and other applications. So what we're doing is taking technology which is mature in transport applications, but maturing it for an aviation application. So this each of these fuel cells is about the length of this desk and about half the width of this desk. So they're fairly big, but that produces 200 kilowatts of power per stack. What we're integrating to the aeroplane is just the fuel cell stack, so the bit where the magic happens. When you see a fuel cell engine, you will usually see one that has what's called all of the balance of plant around it. We have all of our own customized balance of plant, because the balance of plant that you have on a fuel cell engine for ground use is optimized to operate at sea level. It can't operate at altitude. It can't operate in the aviation environment. So how do we install the fuel cells in the nacelle? So that's the engine cell in the partially built state. So what you see at the front there is the structure where the electric motor is going to be mounted, and the spinner for the propeller. The fuel cells are mounted vertically in three rows in parallel behind the motor. So where you can see that aluminium housing, the fuel cells are mounted vertically as a sort of cassette into the bottom of that structure that sits there behind the motor, and in front of the front spar of the wing, and within the original strutted structure. So those black struts you can see, those are the original struts on the Dash 8-300, which pick up the gearbox, the propeller gearbox for the Pratt & Whitney engine. So the fuel cells mount into that structure vertically. Now the second big part of the system is the air management system. To make a fuel cell work, you have to provide it with oxygen. The PEM fuel cells, so low temperature PEM fuel cells, they produce direct current from oxygen and hydrogen. We need to provide the fuel cell with oxygen or air at around 2 bar of pressure, absolute pressure, right up to 25,000 feet. So we have a custom designed turbo compressor which recovers some of the waste energy coming from the fuel cell exhaust to drive the compressor and reduce power consumption. And this is a dedicated compressor that supplies air for 6 fuel cells. So there's a single air circuit which is supplying air for 6 of the fuel cells. In our 2 megawatt powertrain, there are 2 of these compressors per powertrain for redundancy. So that's where the compressors sit on the Dash 8. So this is aft of the rear spar. This is where the exhaust from the Pratt & Whitney engine would be exiting on the Dash 8. We have the compressor and some of the high voltage electrical system in the rear part of the nacelle there. So probably the biggest challenge we have is the thermal management system. As I said, we have to get rid of, even on this powertrain, we have to get rid of nearly 1 megawatt of heat. And we have to do that up to ISO plus 25 temperatures at sea level. In fact, flying in December, it'll be easier because we won't have ISO plus 25 in Moses Lake. Basically, this is done using ducted microtube radiators. So they're the sort of radiators you would find in the side pod of a Formula One car. And we have an active flow control system through the ducts, because for drag reasons we need much less air through the ducting in cruise conditions than we do at takeoff. So the system is sized by the single engine failure case where the aircraft takes off and loses an engine at takeoff. But once you get into cruise, where the airflow, where the speed is higher and the temperature is lower, you reduce the amount of flow through the cooling system. So that's what the radiators look like. That's a radiator that you can see there that's mounted at an angle on either side of the nacelle structure. And the next one shows you the ducts that you need. So those are the cooling ducts that you need to feed those radiators with enough air to produce a megawatt of cooling in takeoff conditions. Those ducts are probably a little bit oversized for the flight test aircraft, but they are pretty much representative of the size of ducting that we will need for the 2 megawatt powertrain. So if you've seen any other fuel cell powertrains that are being tested with cooling ducting that is any smaller than this sort of size, they are not cooling a megawatt of fuel cells with ducting that is significantly smaller than this. You have to design around a very significant amount of cooling air, and there really is no way around that. And the biggest challenge for us there is obviously minimizing the amount of drag that additional cooling generates. Okay, so the last thing I would say, which is a challenge, is what we call our heat MS controller. It's how you control all of the systems that produce the thrust. This is essentially the powertrain FADEC. This is what controls everything on the powertrain. Everything from the power source coming from the fuel cells. So we're controlling the fuel cells. We have a small battery on board which is used just to start the system. So there's a small battery which is used to start the fuel cells. But once the fuel cells are running, the battery is disconnected from the high voltage system. And we have to do a lot of management of air, preloading the compressors in order to get the transients that we need from an aviation powertrain. So the engine has the fuel cell engine has to react in the same time and with the same response characteristics as the pilots are used to from a gas turbine engine. So that's a lot of what we're doing with the software. It's controlling everything from motor torque demand, propeller pitch and speed, the compressors, the cooling system, and the hydrogen supply. This is where a lot of the know-how is being developed. And this is one of the reasons why we wanted to get this system flying as soon as possible, because we need to develop and learn how this system actually operates and where the challenges are. I've been involved, I think, now in 5 flight test programs since I started out the first one 25 years ago with Dougie. And I don't think I've been involved in a single flight test program yet where we haven't discovered things during flight test that we didn't expect. So you always discover new things when you fly something. So the sooner you fly it, the sooner you discover the problems that need to be solved, and the sooner you can fix them. So a year ago, that was the Dash 8 300 that we bought to convert into the flight test bed that will fly later next month. So that photo was taken, I think, in around February this year, when there was snow on the ground in Moses Lake. I know it looks like that looks like a rendering, but it's not. It's actually a photograph of the aircraft, and that's the same aircraft that you saw in the earlier pictures. And you'll see it again in the next month or so, but with that right-hand engine converted into the hydrogen fuel cell powertrain that you saw earlier. So maybe just to finish by saying, what are we doing this for? We're doing this to offer conversion kits to support the conversion of an ATR-72. The ATR-72 is by far the dominant regional aircraft in this market. There are more than 800 of those aircraft out there flying today. It's still in production. So what we're looking to do is install a 2 megawatt powertrain, which is really, as I said, just that it's really just double the installation that we have on the Dash 8-300 flight test aircraft with a propeller reduction gearbox added. And as you can see from the chart there, the hydrogen tanks, the liquid hydrogen tanks, go in the rear of the fuselage with a big module loading door, which is just like a cargo door. The modules are loaded into the aircraft in the same way as you would load LD3 containers into the lower deck of an A320, for example. And then we have all of the powertrain components that you saw earlier integrated into the aircraft. And the other picture on the right-hand side shows what the aircraft will look like. It'll have a very specific look to it with the cooling system, and we're looking to have an aircraft, a converted aircraft, which will have a reduced passenger count. So we take an aircraft that today flies with around 68 passengers on board. With the hydrogen conversion, it has a capacity of 56 passengers. And it still has a range of around 500 nautical miles. So that's less than the current airplane, but 500 nautical miles covers 99% of flights that are operated with this class of aircraft. So that's what it looks like in terms of a layout. You have a 56-passenger cabin and 2 hydrogen modules mounted in the rear, and then a baggage compartment at the rear of the aircraft. The real key, though, to this conversion is that we're looking to make a conversion which is not reliant on so-called eco warriors to make the economics work. We believe that we strongly believe that passengers will be prepared to pay a premium to fly with zero emissions. And I don't know how many of you have talked to your, the generation. I talked to my son's generation, and they have a very, very different view of aviation emissions than maybe I do or my generation does. They certainly want to have the option of flying with zero emissions. But what we're showing here is that even with a reduced seat count, by 2025, we can achieve an equivalent cost per seat kilometer to the Jet A1 powered aircraft. So we have less passengers on board. So the crew costs and things like that are larger per passenger. But one of the big advantages of this type of powertrain, there are very few moving parts. There's no hot section, so the maintenance costs of the powertrain will be lower. And the fuel cost will be lower because by 2025, you can see from these charts, we expect hydrogen. In 2025, we expect hydrogen to be slightly more expensive than Jet A1, but because we have a much better fuel efficiency, much better efficiency of the powertrain, the actual cost per per passenger kilometre of fuel is lower. So we expect to be able to achieve equivalent seat mile costs to a kerosene-powered aeroplane by 2025. And as you see, we expect the cost of dinosaur juice or Jet A1 to rise with time, particularly as carbon offsets are added, or SAF blends are imposed on the industry. And the cost of green hydrogen will continue to come down as the cost of off-peak renewable energy reduces. So that's everything I had to say. I think I can open it up for questions. I think there's probably a lot of questions that people have, and I will do my best to answer them.
Thank you, Mark. As I said at the beginning, very relevant, I think, to what's happening at the moment in the world. So, any questions? I mean, I've got one I'll maybe start with. Just a very simple one for me. Would you expect the baggage handlers of today to be the same people who would load these modules, or would there be specific training required?
So we expect there to be specific qualifications required for the people loading modules. Well, loading modules is not the complicated bit. The complicated bit is connecting them. So as you can imagine, these modules are an integral part of the certified aircraft. So they are the fuel tanks of the aircraft. They also contain electronic systems. So they contain the hydrogen leak detection systems and so on, which are a critical safety element of the aeroplane. So what we're doing is we're changing a certified LRU of the aeroplane. So there will have to be some licensed engineer sign-off of the swap, but the key will obviously be making it as foolproof as it can be. But that's certainly something that will be there from the from initial entry into service. What we are looking at with the FAA is the potential ability to do some of this. Some of the sign-off, for example, remotely, which is something that people have learnt to do, during COVID. The FAA have learnt to do remote air crash investigations during COVID. So if we can investigate the causes of air crashes remotely, then we can probably certify the correct installation of a fuel tank module remotely as well. But yes, it will require some testing and sign-off, as you would do if you were swapping any other module on the aircraft today.
Is it 2 modules or so?
It's 2 modules, yeah. So the ATR-72 has 2 modules. So we have about 340 kilos of liquid hydrogen on board, and each module with the liquid hydrogen on board weighs around 600 kilos. So it's 1,200 kilos total of fuel and module. Which is around a 28% mass fraction. Once you get to a 36% mass fraction, you have exactly the same amount of fuel and module on board as you would have kerosene. So we're pretty close in terms of mass of the fuel to the mass of the fuel that you would be carrying for the same mission.
Any questions?
You must have faced quite a lot of constraints in terms of retrofitting to an existing aircraft, because you've also got to fit into the current nacelle, etc., etc. Do you envisage a time when this is proven technology that the whole configuration of a plane may alter, and that would actually give you greater opportunities in terms of range and scope and other things like that?
Yes. So the reason why we're focusing on the retrofit is, we recognise that we need to have what Paul calls a permissionless business model. We needed to be able to generate demand at the same time as we offer the infrastructure solution to airlines to supply them with hydrogen, which is why we're looking at a converted aeroplane. Longer term, we would obviously like to convince ATR that this should be something that's offered as a retrofit solution, as a line fit solution for future new production ATRs. But if you look more fundamentally at what you would do if you were designing a new aircraft, you would not design it with 2 engines. You'd design it with at least 4. If you design a 4-engined aircraft, we could put 4 of almost exactly the powertrain we're flying on the Dash 8-300 on the ATR, and we would have enough power and better redundancy than we have with a 2-engined airplane. The switch to electric propulsion fundamentally changes the paradigm of the scaling of power and weight. The reason why we have twin-engined aeroplanes everywhere in the world is simply because as you scale a gas turbine, it doesn't. If you double its size, it doesn't double in weight. That's why we have twin-engined aeroplanes. With electric machines, you double its size and it almost exactly doubles in weight. It's almost a linear scaling, which means you would almost certainly end up going back to distributed propulsion with an electric aeroplane.
Well, hello. Considering you already implanted a new powertrain system in an originally existing aircraft, will it not add more weight to your airplane and you will cross the threshold of maximum takeoff mass?
So yes, it does add more weight, but in fact that's one of the constraints we have. We have to remain within the existing maximum takeoff weight of the aircraft. It is a challenge, but with the 56-passenger conversion of the ATR-72, we can still operate the aircraft with 56 passengers and a 500-mile range just within the max takeoff weight of the existing aircraft. So it's doable, but it's a challenge.
Thank you.
But that's always the case with every aircraft I've ever been involved with.
Okay. Thank you, sir, for the presentation. It was very interesting. I'm studying in Cranfield University of Aerospace Vehicle Design, and I wanted to ask, as it was a retrofitted aircraft, that the thing you presented. So you said on the right-hand side will be a Pratt & Whitney turboprop engine, yep. And on the left-hand side is going to be retrofitted with the new hydrogen proposed powertrain. And I was wondering if you add additional, you change the existing nacelle with the 2-ducted fan module, which has a different propeller also.
Yeah.
And
so this is an experimental aircraft. Yeah. This is just the configuration we'll fly as an experimental aircraft. So it's an asymmetric aircraft. Yes, it has a different configuration on one side to the other. But yeah. when we do the conversion on the ATR-72, both sides would be converted to the hydrogen powertrain.
Is it correct if I understand that this is a flight test aircraft that's gonna commit to a flight test with
yes.
this asymmetrical configuration?
Yep. It's a flight test aircraft. It's certified with the FAA under what's called an experimental type certificate. So it's a one-off experimental type certificate that we fly the hybrid configuration with.
Okay. So because this is a retrofitted aircraft, you changed a nacelle with a new system. So was there any structural changes to the wing structure?
Almost none. On the ATR, when we do the conversions on the ATR, we'll do them with what's called a supplemental type certificate, which is a means of modifying an existing aeroplane. There will be some modifications to the local attachment structure of the wing, but not significant. The overall wing bending moment is almost unchanged. So we don't see the need for significant structural modifications.
And
The
also
biggest
with the
modifications are to the fuselage for the introduction of the new door and the relocation of other components.
is it okay if I ask you one more question? It's just a very simple thing about the because the picture you showed with the modular hydrogen tank that's going to be fitted inside as like a cargo, it was shown depicted as a semi-spherical type, and the next presentation slide that you showed was a spherical cylinder shape.
The module that's loaded into the aircraft is the shape that you saw there on the pictures. Within that module is a spherical tank which contains the liquid hydrogen, but there's also a whole load of other components like valves and heat exchangers and other components within that module envelope that you saw in the pictures being loaded into the aircraft.
So is it correct if I understand that inside the module there's going to be a cylinder type hydrogen tank
and a whole load of other systems equipment as well.
And also, if you want to inspect that cylindrical type of tank, how would you open the tank open? How would you open the tank and inspect inside part?
You don't inspect inside the tank. You don't need to inspect the inside of the tank. They have a defined fatigue life. But you can inspect inside the module. The module is easy to open. It's just a lightweight cover. Yeah.
How do you inspect the outside of the tank?
The module is literally just a thermoplastic cover that goes over the top of the module and covers all of the the equipment.
So I was wondering about inside the fuel tank itself, inside the hydrogen tank itself, but if you don't inspect it. Okay.
No, you don't need to inspect.
Good evening, sir. My name is Michaels from Cranfield University, Aerospace Computational Engineering. Sir, concerning your presentation, from the look of it, I saw both engines are different, maybe because of the flight testing. So what about in future when these aircraft come to service? Are we still going to have different engines, or will have the same engines?
No. When it goes into service, it will have the same engines on both sides.
Okay, sir. And if we have the same engines on both sides, then what will happen to the integral part of our wing? Is it going to be empty, or is it going to be filled with something? Because looking at the conventional aircraft of maybe this ATR 72 or thereabout, the wing usually carry the Jet A1.
Yep.
Yes.
No,
so
the wing will be empty. The wing will be dry. You can't carry liquid hydrogen in a wing structure. So it's we don't have a use for the space in the wing structure.
Okay, sir.
So
Thank you, sir.
it becomes a dry wing box.
Okay.
Considering there's a sorry. So considering that like the modules, like the fuel cell stacks degrade over time, so what's the life expectancy we are getting from the stack that you guys are building?
So a fuel cell stack its life really depends on how well you cool it. If you keep it at its design operating condition, then the fuel cell stacks themselves have a very long life. In some ground applications, they can last up to 20,000 hours. We're expecting in an aviation application for them to last closer to 8,000 to 10,000 flight hours between replacement.
Thank you.
And does cost become an issue? Cost of replacement?
Yeah, I mean, the maintenance cost of the powertrain essentially just becomes a case of amortizing the replacement of the components, the replaceable components over the lifetime of each of the components.
Hydrogen
The hydrogen fuel cell powertrain has a lower maintenance cost than a gas turbine. Because
so the module replacement is that balance with that maintenance delta of the powertrain.
yeah.
As you said that you're using the modern electric engine such as this Magni 650. So by removing of the gear reduction box, how can you reduce 1 megawatt of power?
So we for this aircraft, we're running this motor is capable of a bit more than 750 kilowatts, but 750 kilowatts is about the maximum power we can operate at without a propeller reduction gearbox. But for the production version, we will have 2 megawatts of power driving through a propeller reduction gearbox and driving a bigger propeller that will turn at much slower speed. So this propeller is turning at about 2,300 RPM. The propeller on an ATR has to turn at around 1,200 RPM because the propeller is bigger. So to keep the tip speeds down, you have to turn it slower. And that's essentially why you need a propeller reduction gearbox. You can't realistically design an electric motor which turns as slowly as 1,200 RPM.
Good evening, Mark. Thanks for the talk. Very much well worth my trip down from Cranfield this morning. I'm Craig Lawson. Having done some similar work, I'm very reassured to see your big, ugly heat exchangers on the side of the aircraft. Have you been estimating the ram drag?
Yes.
Do you find it a big drag, and did it cause you to uprate the power from the propulsion system?
So yes, there is. It's a factor, and we do need to add a little bit of additional power for the to account for the ram drag. It's a factor. It's not huge, but it's a factor that we have to control very carefully by careful design.
Right, have we got time for maybe one last question? I'm just aware of time's moving on.
One question and then last John.
Neil obviously has lots of questions.
Thank you for the presentation. It was quite nice. So one of the questions I had was, you said the fuel will be removed from the, general aviation fuel will be removed from the wings as you're using the hydrogen which is stored in the fuselage. So we know the fuel in the wings actually helps in balancing the CG and other stuff, and it also acts as a damper for aeroelastic effects of the wings. So what kind of structural changes do you think we will need to make in the plane to keep all these under check so that the plane doesn't stretch?
In terms of overall structure, we're removing the fuel, but because we have a heavier engine, the overall wing bending moment is more or less unchanged. There's a slight increase in wing bending moment on the outer wing. The outer wing of the ATR-72 is actually a composite outer wing. And at the moment, we don't think we have any significant issues with aeroelasticity. This type of aeroplane is not as challenging as some swept wing aeroplanes would be from an aeroelastics point of view. So there will be local reinforcements around the attachment structure, but we don't believe we will have to make significant reinforcements to the wing as a whole.
Okay, thank you very much. Thank you, Mark. Thank you for your questions. John, would you like to say what you've got, please?
We haven't quite finished yet, Mark. I had a question, but I better ask you later. I'm the president of the CCAAA, and very pleased to, as Craig said, to come today. It was more than worth our while. We've been involved at Cranfield doing environmentally friendly aeroplanes since the mid-80s, and looked at all sorts of things, and this is really a tremendous addition to that process. I'm conscious that many urban air mobility aeroplanes are looking at fuel cells, and maybe when you finish sorting this out, you might sort out a good urban air mobility that will get us from Hendon to Hamilton Place in less than an hour and a half. But that was a effect we had. Other thing to say is we've got some little presents for you. We've got a high quality Cranfield pen.
Thank you.
More important, we've got a model of our new aeroplane, the Saab 340, our flight test aeroplane. So perhaps you can electrify that as well.
Yes. Well, the flight test pilot that's flying our Dash 8300, Miguel, he's done a lot of flight testing on the Saab 2000 for a military version for the US for the US military. So.
Interesting aeroplane. But I think on behalf of everybody, I'd really like to thank you for seeing some real engineering. It's been really good to see that. Nothing too high for well, it's very sophisticated, but not pie in the sky when you die. So thank you very much for a great lecture.
Thank you.